Let's talk about AI. It's obviously smart, right? Incredibly smart. It can write code, it can create art, but there's this giant catch, a hidden weakness. AI is smart, sure, but it is unbelievably inefficient. So why is that? And more importantly, what are we going to do about it?
Well, today, we're going to dig into that why, and we're going to explore a pretty radical solution, one that's been hiding in plain sight for millions of years, the human brain. We're talking about neuromorphic computing, which is basically a revolutionary attempt to build actual brains on a chip.
Okay, so to really get where we're going with this, we first have to understand the problem with where we are right now. Current AI, for all its power, pretty much runs on brute force, and that comes with a seriously heavy price.
And this quote right here, it absolutely nails the issue. Today's AI has, in a way, memorized the entire internet, but it doesn't really get it. It just recognizes patterns. So when you throw it a curveball, something it hasn't seen before, it gets brittle. It kind of panics. It just doesn't have that real human-like ability to adapt on the fly.
When you put them side by side, the difference is, well, it's kind of shocking, right? Traditional AI just devours energy and needs these mind-bogglingly huge data sets to learn anything. The human brain? It runs on the power of a dim light bulb. It can learn from just one or two examples, and it's incredibly dynamic. So the big question is, why is there such a massive gap?
Well, the answer goes all the way back to the basic blueprint we've used to build computers for the last 75 years. It's called the von Neumann architecture. And in this design, the processor, the part that does the thinking, is physically separate from the memory, the part that remembers stuff. So to do literally anything, data has to be constantly shuffled back and forth.
Now, for something like AI, which is always crunching these gigantic data sets, that constant back and forth creates an epic traffic jam. It's called the von Neumann bottleneck, and it is the main reason why AI is so slow and so power-hungry. It's a physical speed limit that's baked into almost every single computer on the planet.
So if the old design is the problem, where do you find a better one? Well, researchers started looking at the most efficient computer ever created, the one right inside your head, nature's very own supercomputer.
And this led them to a really simple but kind of profound question. What if we stopped trying to run brain-like software on computer-like hardware and instead just copied the brain's hardware design from the get-go?
And this is basically the blueprint. Up top, you've got the real deal, the biological brain, with its neurons and the synapses that connect them. And down below, that's the goal, a chip with artificial neurons and artificial synapses. The whole idea is to create a direct, one-to-one copy of the design.
This whole approach has a name, neuromorphic computing. It was actually coined way back in 1990 by the brilliant Carver Mead. And the goal is simple, really. Build chips that are literally shaped like our nervous system so they can achieve that incredible efficiency and adaptability we see in nature.
So how does this actually work? Well, it pretty much boils down to three key ideas. First, spiking neural networks. So instead of a constant fire hose of data, information is sent in these little discrete spikes, just like real neurons. Second, because of those spikes, you get what's called event-driven processing. The chip only uses power when a spike actually happens. If there's no new information, it just chills out, using almost no energy. And third, massive parallelism. Instead of one really powerful processor, you have millions of simple ones all working together at the same time, just like the billions of neurons in our brains.
Now, this isn't just some sci-fi concept on a whiteboard. Nope, this is happening right now. Some of the biggest tech companies and universities are turning this biological inspiration into actual, real-world silicon.
I mean, just look at what's already out there. You've got IBM's True North chip, which packs 1 million programmable neurons. Then there's Intel's Loihi, which is amazing because it can actually learn on chip. It adapts without even needing to connect to the cloud. And the Spinnaker project is built just for massive, large-scale brain simulations. These are real functioning pieces of hardware.
And the results are, honestly, they're just mind-blowing. Get this, that number, 1/10,000th, that's the power density of IBM's True North chip compared to a normal processor. It is 10,000 times more energy efficient. That isn't just a little improvement. That is a complete game changer in computing.
Okay, so what does this all mean for us? I mean, what does a world with computers that are thousands of times more efficient actually look like? This is where things start to get really interesting.
For starters, this is going to completely change the game for robotics and any kind of autonomous system.
especially for something as life-changing as brain-machine interfaces. With a neuromorphic chip, a prosthetic limb can process your neural signals instantly, right there on the device. This means you get this intuitive, adaptive control that feels less like a tool and more like a real part of your body.
But it's not just about these huge, complex robots. This tech is also going to make our everyday gadgets truly intelligent and, well, just amazingly efficient.
This is what unlocks the true power of something called Edge AI. So imagine smart sensors that can run for years, literally years, on a single tiny battery. Or your phone doing instant image recognition without ever sending data to the cloud. You could even have wearable health monitors that are constantly learning and adapting to your own personal body chemistry. All of this intelligence lives on the device, not in some faraway data center.
Of course, we have to be realistic here. It's not all smooth sailing. Like with any technology this revolutionary, there are still some pretty big hurdles to get over before this stuff goes mainstream.
The biggest headaches right now are actually on the software side. We don't have those easy-to-use universal frameworks like TensorFlow or PyTorch that power most of today's AI. Programmers have to learn totally new ways to think and to code for these systems. And right now, every company's chip is a little bit different, which makes it tough to build software that can run on everything.
But the motivation to solve all these problems is immense, because the ultimate goal here, it's really profound. It's about so much more than just making faster computers. It's about finally bridging that gap between how living things think and how machines compute.
Which leaves us with one last really fascinating question to chew on. For decades, we've tried to make our own brains work more like computers, be more logical, remember more things. But as computers finally start to work more like our brains, becoming intuitive and adaptive and efficient, how is that going to change what it means for us to think?